Okay, just out of curiosity, I'm just curious who's here.
So this is our second seminar on P and NP problem given by Dr. Buckles. This is our Y0 Physics Seminar. This is the second part, so he's probably gonna start from summarize what he talked about in the first part. Hopefully today he's gonna finish.
Sure.
Okay.
This is gonna be short because I just wanted to add a little bit.
Okay. And again, we appreciate you showing up, and we have another one later this semester. And in case you're interested in joining the physics club, talk to me or talk to Chase. He's on the Zoom, I think. He's the president right now. So anyway, without further ado, let's.
Okay, so yeah, so I only need to summarize a little bit, from last time because this topic is a little bit of a different focus, from what I was doing last time. So, so the stuff I need to review this time is just to remind you guys what a Turing machine is, which is kind of a mathematical abstraction of a computer. Okay, so for you guys that were here last time, do you guys remember the things that Turing machines have?
It has infinite memory.
Yes, correct. Okay, so let's write that down first. So basically, a Turing machine, there's this underlying assumption that the Turing machine has an infinite amount of memory. And basically, if you want to input information into the Turing machine, you have to write in the symbols. In this case, you can write in zeros and ones into memory. Now, last time, even though the simplest Turing machine, you would just use zeros and ones. Last time, for convenience, if you remember, we're assuming our Turing machines can handle zeros, ones. Eventually, in the last talk, we generalized the concept slightly to say, just for convenience, let's assume you can read it.
Stop sign.
Yeah, so basically, it's like we'll assume our Turing machine can handle the simple zeros, ones. We had like a triangle, and then do you remember the other one?
You were not there?
He told me he was here.
I can't remember the square. I'm not sure.
Well, I'm writing it as if it's a square, right? But it's a blank.
Okay, blank.
Yeah. So if you want to input some information and then end it with a blank, that's a good way of saying this is the end of the input. Because if you don't have a blank, it's pretty hard to know, like, where does the input even stop exactly? I mean, there's ways you can handle that problem, but the easiest way is just to assume, okay, you'll put in some ones and zeros. Then you put a blank, and then everything from then on will be blank. And then if a program's running, it will assume everything that comes before the first blank is the input the data for that.
So what does the triangle do?
The triangle is something we'll allow a programmer to use if they want to. We'll just say if they want to read and write triangles to memory while trying to solve some underlying math problem.
Okay.
Right, or while running the program, they can optionally use the triangle. They do not have to use it, to do anything. The main thing we did was a blank so that it's easy to determine like where does the input end and stuff like that. Okay, so anyway, you have a Turing machine that has an infinite amount of memory, and then what's the other thing? So you can put as much.
We talk about two kinds of problems. One is the P problem.
Sure.
Which you can solve by polynomial type. And then this problem basically runs like in a sequence, like you go one, each time is like there's a definite path of start from the very beginning of the program to the end of the program. And then we have this NP category, which is a non-deterministic. I forgot what the P stands for.
It stands for polynomial.
Yeah, non-deterministic polynomial, meaning that in your program there will be cases that when you can branch out, basically. It's like flipping a coin or whatever. Well, in the real machine, because there's nothing like you can do with flipping coins. So what we do is you just copy what is going on and then just branch out. Like it literally go two different ways.
Yes.
It's like parallel universe. In the end of the day, you have a bunch of different.
Yes, that's right. Now, last time I talked a lot about these two classes, P class problems and P class problems. For this lecture, I wasn't going to concentrate on that so much. I was going to concentrate on just something that's kind of interesting that's related to these Turing machines.
Like example, right?
You'll see. So I was going to concentrate. Well, anyway, I'll get to that in a second. I was going to concentrate on this concept of a computable function, like what functions are actually computable, by programs. And you don't need to know much about like these classes, to actually understand that problem. Anyway, so yeah, but what about the Turing machine itself? So the Turing machine, it has available to itself an infinite amount of memory, but then the other thing a Turing machine has is a Turing machine is always,
Because of
it's always running
program.
a program, right? And if you remember last time, I had the programs written out as graphs. Essentially, the graph was like a code for the program. Okay, so one of the programs I had last time, this is just an educative example, so it's a super simple program, is this S here, this program, it either means to start running the program from that state, or it means to stop running the program, finish running the program. And how do you know which one it is? Well, a start has arrows going kind of away from it, and a stop means, while you're running the program, you reach this. Programs are allowed to branch based on what they read. So, the read head starts at the beginning. In this case, if this was the data, and let's say the rest of it's just all blanks, it would read a 0. So if you want to read, if the program reads, it can branch based on what it sees. So if it reads a 0, the program goes this direction. If it reads a 1, it goes this direction. So just to remind you, if you have a 1, this either means that the program just read a 0, or it means the program should write into memory a 0. How do you know which one it is? It's based on, did it just branch? That means it just read a 0. If it didn't just branch, that means it should write a 0. One is kind of similar. Sorry if this is boring if you saw it before, but I'm assuming somebody.
I already forgot.
You already forgot it? Okay, so in case somebody didn't see the first talk, but if you saw the first talk, you might think this is boring. Okay, so in this program, if there's a 1, it means the program just read a 1, or it means to write a 1, and that's context dependent. So in this case, the program would branch this direction based on a 0. And then what this program does is it gets to the next stage where it moves the read head to the right. So an R means move the read head to the right. Okay, so in this case, the read head would go to there, right? Okay, now I'm going to branch from this point. Okay, so which direction do you think this program is going to go?
So when it sees 1, right? So you read the 1 then, right?
So it would go this way, right?
And then it stops there.
No, it's not gonna stop. I just haven't finished the program. Okay, so from here, it's gonna branch. So basically, when it reads this 1 here, right? It's gonna read the 1, and it's gonna oh, it's not gonna branch here. Sorry, made a mistake there. Okay, so then it's gonna move the read head to the right. Okay, so this read head will go here. And then at this point, it's going to branch based on what it sees. If it reads a 1, it's going to stop. And if it reads a 0, it's also going to stop. Can you guys online see the bottom of the chalkboard, okay?
There might be some.
Oh, they might be muted.
Or they didn't say anything, but can you see there's some thumb up there telling you that.
Oh yeah, they can. Okay, so that's good. Okay, so now in this program, I never actually used an L, but of course, if you had seen an L, that would be a code for move to the left. And for the problems we worked on last time, the so-called P class of problems and NP class of problems, the input always represents some kind of math problem the program was tasked with trying to solve. And the math problem always had to have a yes or no answer. It had to be a so-called decision problem to be, class P, right? So the program would always say, yes, this math problem has a solution, or no, it doesn't. Kind of like is a certain number of prime, that's kind of a yes or no answer. And then the output for the whole machine would just be like, what does the read head end up over? And if it's a 0, that would be the output that represented no, the number's not prime, or depend on the problem. Or if the read head ended up over a 1, that would represent yes. Okay, so whatever program we write here, it's always going to give an answer of 0 or 1, the overall program. So in this case, let me change the input a little bit and ask you guys, what's going to happen if the input was 0, 0, 1, 1?
So it's gonna start, so you'll start from beginning, right? So
it'll start from the
it's
beginning.
gonna get 0.
It'll
and
see
then-
the 0.
Then you move to the right, you see another 0, and then it will still move to the right, and then you see a 1.
That's correct. Okay, so it'll see the 2 zeros, and eventually, when it does see its first one, it'll go over here.
Yes, and then it will move again to the right, and then you see 1, and then it'll stop.
Yeah, and so what I wanted is if it saw 1 to give an answer of yes, and if it saw 0,
It stops anyway, right?
it stops anyway, because I wanted it to give an answer of no. This program is inefficient, but what I was trying to do is the program's trying to figure out if there's 2 consecutive ones
Uh-huh.
in the input. So if there are 2 consecutive ones in the input, this program's smart enough to recognize that. If there are not 2 consecutive ones in the input, like if there's 0, 1, 0, 1, then this one would come out with the
No,
no, right?
but the problem is like, you may stop at the first 0, but there might be some 2 ones in the further down, but you couldn't see that.
Oh, okay, so let me, what's the input that you're asking about?
I'm saying that, you say you have 1, and then you have a 0 next to that. Let's say the third one, no, let's say, keep the first 2 0 there. The third one is 1, the first one is 0. And then say there might be two ones like in a row.
Oh,
But-
sure,
But
sure.
then it's gonna say no, right? Because it's
Yeah.
gonna stop the.
Yeah,
but
so
it's gonna
so that's
stop it.
exactly right. So what this program does is it doesn't detect 2 ones anywhere.
Uh-huh.
It detects if there's 2 ones somewhere in the initial segment at the
Right,
beginning.
yeah.
That's all it does. It doesn't do much, right? It's a very simple program. Now,
So I have another question. So
Uh-huh.
basically, how do you store this program? It's like a punch card you use? It's a punch card you bring to the computer, kind of like punch card, you know what I'm talking about, right? Is that the way that how you show the computer the program, like by running a punch card or something?
yeah, you could. I mean,
Essentially,
if there
or
was a
something
way to
like-
translate the program into a punch card,
Uh-huh.
then yeah.
Or something like punch card, right?
Oh yeah, but you know,
Or
on modern computers, you could just type in your program.
Yeah, but
This-
this is not modern computer, this is a turning machine.
This is a Turing machine. Yeah, and I didn't think about this because, you know, I should have prepared this part of the lecture a little tighter. This one, I had given this example last time when we didn't have the concept of triangles or blanks, right? And this program will work perfectly well if you just, you know, initialize all the memory to zeros and then initialize some initial segments to zeros and ones. But technically, we may need to deal with the case where you might read a blank, you know, at some point when you're branching. So, you know, since I never had a specific branching for what if you saw a blank, in other words, I should have stuff in here like anytime it branches, I should also consider the case where you might have seen a blank, right? And then what do you do if you see that? So I want you guys to understand that if you see something for this program, we're just gonna have this understanding that if you see anything other than a 0 and 1 at any point, you'll just stay at your same state, right? So could this go into an infinite loop then, sort of?
It
Yeah,
could be like it's 0 and R, right?
yeah, so
Or-
what's an input that would cause this one to go to into kind of an infinite loop?
So you never move to 1.
If you never see a 1, like
Yeah,
let's
yeah.
say it's 4 zeros and a blank,
Yeah.
then what'll happen is we'll see a 0, it'll move the head, read head right, it'll see another 0, move the read head right, see another 0, move the read head right, it'll see another 0, move the read head right. By the time the read head gets to here, it's gonna see a blank. I never told it what to do if it saw a blank.
Oh,
So I'll just say, if I didn't tell it what to do, it better rerun this line of code.
then, okay, the blank don't cause it to be.
That would cause it, yeah, if you have some zeros and blank, that would cause you to just keep rerunning that line of code, that move to the right, move to the right. And so in this case, there actually are some infinits, you know, all zeros would never hit that first one, or effectively, you know, would go into an infinite loop. That could have fixed that, knowing that it might read a blank at some point. I could have gone ahead and given it what if you read a blank, then go ahead and stop and say 0. That would have kind of fixed it, you know. But I just want to kind of keep it the program a little simple. Okay, so if this is a program, is there a way to translate the program itself into a bunch of zeros and ones? So what's your intuition? Somebody gives you a program, which they'll give it to you as a graph. Do you think you could always translate it into just a bunch of ones and zeros?
It should be, right?
Yeah. I mean, in real life, programs can't get translated into machine code, you know, that's just all ones and zeros, you know, in real computers. So, I mean, I could just ask you to take my word for it that, yeah, whatever the graph is, you could store the zeros and ones. But I thought I'll just go ahead and find a way to code it just to convince you. And we'll assume our program never branches on blanks or triangles, just to make it even more conceptually simple. Okay, so if you want to code this program, you're going to need to give numbers to all the states. So you might call this state 1. You might call the, and you don't need to number the branching ones because at the end, when you branch, it's just kind of telling you where ultimately to go. So we could call that one state 2. We could call this one, this is a branching situation. We call this one state 3. This is a branching situation, so we don't need to number it. We could call this one state 4. We could call this one state 5. Okay, and see if you guys kind of follow my logic here. So what does state 1 do? Yeah, basically, it branches based on whether it sees a 0 or 1. And so if it sees a 0, it's going to go into state 2. So the way I coded this is sometimes some states will have to do things like move the read head right, move the read head left. Sometimes the state will have to write a 1, write a 0. This program never writes anything, but a program could write those things. So I thought, okay, I'll have a number that represents the state. Then if the state only branches, doesn't really do anything else, I'll put it in there as a way of saying do nothing. You know, that's a special code for nothing. And then state 1, if it reads a 0, it goes to state 2. If it reads a 1, it goes to state 3. That's how state 1 works. Okay, then we'll put a colon here. Okay, how does 2 work? So if you're in state 2, the program is supposed to
0 stays in state 2.
Yeah, it branches, and on 0 it stay in state 2, and if it sees a 1, it will ultimately come over here to state 3. Okay, so let's go back that down here, a 2 and a 3 here, and then does it actually, do we need a code to represent anything else that state does? I think you're missing the letter R. Doesn't that state, you know, when you reach that state, doesn't it move the read head right before it branches? So what does state 2 do? It moves the read head right, and based on reading a 0, 1, will ultimately branch into those locations. Okay, now what does state 3 do? That's the state here.
Okay, R.
That's right. It likes to move the read head right.
4, 5.
Yes, and if it reads a 0, it goes to state 5. And if it reads a 4, I mean, if it reads a 1, it goes to, you know, state 5, right? If it reads a 0, it goes to state 4. If it reads a 1, it goes to state 5. Okay, what about 4?
4 is 10, right?
Yeah, 4 stops. Okay, so I went ahead and just thought I'll put an S there to say it stops. And I don't, because it's not a branching situation, but I wanted all these things to have 4 symbols or slash numbers and or numbers. I thought I'll just use a little empty set symbol as a way of saying I didn't really have any need for those spots. So if I don't need some spots, I'll just put empty sets. Okay, 5 is very similar. What does 5 do?
Stop.
It just stops. It doesn't branch or anything, so I have no need for this. Okay, so see how you could do this kind of, it'd be very easy to, given any program, could you number all the important states and then just write out what they do and code, you know, it's coded, right? But once you do all that, it's just a linear, no matter how complicated the graph is, you can turn the graph into just a bunch of characters.
Or I can just use plain English.
Yeah, you could use
Right,
English, but you know, that would be boring. Okay. Now, so basically, if I yeah, English is great too. Okay, so if you translate these into symbols, well, then to actually turn the program into, we want to potentially have a program be an input, right, to another program or something. So if you want it to all be zeros and ones, well, I probably better rewrite these numbers, right, as binary numbers so that I don't have as many symbols. I mean, because these numbers could become arbitrarily big, you know, 100, 400. I don't want arbitrarily many symbols. So I could translate this. This is kind of boring, but just bear with me. Okay, so binary of 1's a 1. So it stays itself. Okay, and binary of 2 is, of course, are you guys computer people? You're not? Okay.
1, 0.
No big deal if you're not. Okay, 1, 0. 3 is 1, 1. Okay, and then We have a 2, which is
10.
1, 0, good. Then we have an R,
1 0
a
1
1 0 1 1. Okay, and then the rest of it's gonna be what, 1 1 or 1 1
Oh, 1 1, yeah, 1 1. Then
R.
you need another digit, right? Like, yeah,
That's correct. Okay, so 4 is 1 0 1 0 0 and 5 is
1 0 1.
1 0 1. Okay, good. And then
1 0 0.
1 0 0. Okay. Else. Empty set colon. Okay, and then the end will be 1 0 1. Yes. Empty set. Okay, so now the purpose of going from here to here is to make sure all the symbols are straightforward. What are all the symbols we might be using? Well,
you need to change the letters, right, to some numbers.
That's exactly right. So we've got some letters, some commas, some colons, just to make it a little more readable, right? So we better have codes for all that stuff, right? So I thought 4 binary digits is probably good enough code. So wherever we see a 0, we can encode that with the binary code 0 0 0 0.
Okay.
That would represent 0. A 1 could go with. We can encode that with 4 bits, 0 0 0 1. Everywhere we see a 1, we'll translate that to that. Okay, if you ever see a comma, we'll encode that with this code. If you ever see a colon, we can encode that with that code. If you ever see a S, which will always represent stop, we can encode that with this one. That R could be this one. That L could be this one. An empty set symbol could be this one. And we never needed to write a 0, but if we ever tend our program to write a 0 at some point, I'll say W0 to distinguish that from 0. If the program maker needs to write a 0, that will be the code. This, and if the program maker needs to write a 1, that will be the code. This, right? And if you wanted to add codes for things like reading a blank, or anything like that, you could do it. But anyway, let's just assume well, actually kind of need that. So I mean, really, since our Turing machine works on those symbols, do we have enough symbols for the rest? Writing triangle, writing blank.
Well, I mean, I'm sorry, but are you just trying to imagine language?
Well, I'm just thinking, since our Turing machine actually reads and writes technically 0s and 1s, and even blanks, it could write blanks, it could read blanks, and branch on blanks, it could write triangles, branch on triangles. And technically, if I wanted to allow every conceivable program someone could write, the computer should be able to write a blank.
Yeah, but I mean, as far as you were not exceeding 16, right? You can use this 4 digits.
Right, as long as we don't exceed 16. So I'm kind of wondering, will we exceed 16 if we allow write a triangle, write a blank? Is there anything else up this thing that you guys can see?
I don't know. I mean, right now we have what else
I think we only
we have 10, right? We have 10 right now. Then we can allow to have another 6, right? 6
Well,
or whatever.
we could definitely do this one. Okay, so
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh yeah, 11, 12.
12, and then we have another 4.
Yeah, then we have another 4. But I think as long as we allow the program to write those 2 extra symbols, writing triangle, writing blank, is that good enough? Because if we branch when we see a blank, okay. So actually, we would need to expand this to what do you do if you see a 0? What do you do if you see a 1? What do you do if you see a triangle? What do you do if you see a blank? Right? We'd have to have in our way of encoding program more spots to handle those branchings. So, but you can have them, right? You can expand the notation to include what do you do if you see a blank, have a couple extra numbers. If you don't use some of them, just put empty sets there. So we can include empty set, because we never tend to do anything if we saw those. Anyway, you get the idea, right? So once you do this, basically now any program could just become a bunch of 0s and 1s to represent the program. Now, so that's kind of like the first simple idea is that, but you guys know, I mean, that's the way real computers work, is they store programs as codes that are going to get sent to the CPU, to tell the CPU what to do. And so in real life, that's a real intuitive concept that programs can be stored as data, that represent the program. Okay, so let's say we have a program. And I'll just pretend this was real short here. Okay, so somebody gives a code, somebody gives a string of input that represents a program, like that's the meaning of the input. Then sometimes somebody might write a program that if you translate it back into symbols would not really be syntactically correct, right? Like they might have things like double commas, stuff we would never do when we write a program. So if you want to fix that problem, that some of the strings of input, in fact, I would say a lot of the strings of input don't really represent programs. We can just think, if a program tries to read this program and then it sees that it's not syntactically correct program, we'll just think that inputs like that represent this very simple program that starts and immediately stops. So this is the program that will be for all input strings that are syntactically correct. We'll think of them as representing a simple program, a program that just kind of doesn't do anything, it stops. So what that means is, if you list all the possible inputs that are going to represent programs, so there's the empty input, 0, 1, then what was the rest if you did kind of logical order? 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, okay, etc., right? If you listed all the potential inputs, then wouldn't every single program that you could write exist somewhere? Yeah. And every single input represents a program, even if it just has to be a program that does nothing, right? And by the way, a lot of programs, because you could have numbered, I'm thinking that you number 1 wherever the start is, but the rest of the numbers could be whatever you want. That means that you can number the states however you want. Any one program actually has infinitely many ways to encode itself in the list. So every legitimate program kind of appears infinitely many times, on the list. And then there's a whole lot of these that are syntactically incorrect. They're not really programs. So just interpret this as representing, the program does nothing. Okay, so you can kind of think your list of potential programs is kind of like an infinitely long list that includes all programs. And then all those programs could have inputs. What are the possible inputs? Well, you might have an empty input, or you might input the program the data 0, or a string that's a 1, or 1, 0, or 1, 1, 1, 0, 0, 1, 0, 1. Okay, like this, right? Okay, now if you allow the potential inputs to go basically forever to infinity, then you end up with a grid here that represents every conceivable program a Turing machine could try to run on every single simple input that just involves 0 spots. We're just all the way along input to be simple like that, right? Okay, now what's going to happen? Well, for every one of these spots, the program is either going to return a
0, 1.
0 or 1. And just to make that, I think these empty cases are a little confusing in this case, so let's just not consider this. Okay, so we'll say there's at least one little bit of it, but okay, yeah, so the program will either return a 0 or it will return a 1. Can a program do anything else besides returning a 0 or a 1?
I don't know, it's up to you, right?
Well, oh yeah, but I'm saying, given that we just interpret.
You kind of doing infinite.
Yeah, that's what I'm trying to get at. It is possible that the program, a particular program on a particular input may find itself going into an infinite loop. And therefore, it never really stops. Therefore, it never really, it never gives it the
It's
answer.
like called not halting or something.
Yeah, exactly. It would be like some programs won't halt on some inputs. And so that's unfortunately one of the possibilities. So it's like some programs may give certain answers on certain inputs, but on other inputs, that input may just cause it to go to an infinite loop. But that's pretty much all that could happen. Either the program's failed to terminate and it'll give a 0 or 1, or the program on a particular input will never terminate, and it will potentially give just go into an infinite loop. Okay, so let's assume that maybe you have a program here that likes to return 1s a lot. Maybe this program likes to return 0s and 1s a lot. Okay, maybe this program always goes into an infinite loop, no matter what you do, no matter what the input is. Like this. Okay, so maybe this program does this too. Okay, so when we're talking about the P class of problems, we were really only interested in programs that no matter what the input was, they always came out with like a yes or no answer. You know, they always had to give you an answer. It was supposed to be the correct answer, you know, for that math problem. So those particular programs are a little bit special, the ones that are resistant to going to infinite loops. And when we're studying the P class of problems, we're really just interested mainly in those kinds of programs that always give answers. Never went into this loop. And then within this P class of problems, do you guys remember from last time we talked about the so-called computable functions?
I even remember we talked about
Computable, that was just barely at the very beginning when we started saying, okay, basically, if you look at all programs that will abstractly terminate on all inputs, you can kind of think there's this underlying function that on this input returns 0, on this input returns 1, on this input returns 0, on this input returns 1, you know, and so on. And so basically that implied function from the set of all input strings into 0, 1. If there exists a program that can systematically take all input strings and always consistently give you an answer like a 0 or 1, the functions like that are known as computable functions because there is a computer program that can basically calculate them. And then this set of computable functions, last time I was saying not all functions are actually computable by any program. So let's write that down, not all functions are computable. So let me prove that to you. So why is it that some functions are computable? Well, there's this thing called diagonalization, where you look at what does this program do on its own input. You know, if its own code was its input, and you go down this diagonal, what would that program do if it was fed its own nearest code as its input? What would this program do if it was fed itself? What would this program do? In this case, this program we're imagining maybe that goes into an infinite loop, and so on. So this function, these values here form like an infinitely long diagonal because this whole thing, there's infinitely possible many programs. There's infinitely possible many inputs you can feed to those programs. So you can look at this and you can ask yourself the question, if you try to make a program that would give an answer of 1 on this input, would give an answer of 0 on this input, would give an answer of 1 on this input, would give an answer of whatever on that input, they call it a 0, that's infinity, would give an answer of 1 on this input, so on. Is there a program that could actually do that? So the maps. Okay, in this case, I'll just be suggestive. So the maps of infinite 0. So 1, it maps infinite 1 to 0. It maps an infinite 1, 0 to 1. It maps an infinite 1, 1. This one doesn't matter much, but I'll call it a 0 when I see it infinity. It maps so 1, 0, 0 to 1. And I'll just put etc. to see, like, do you guys get the pattern here? Like, why I'm choosing these numbers? So I'm asking.
So the left is gonna be the programs.
Okay, now by the way, so does there exist a program? Now, does there exist a program means you can choose which program you want to consider. So does there exist a program, which those appear in this, you know, first column.
So this is the mapping that the program I'm trying to do, right?
Yes, does there exist a program that will take these inputs and map them to these outputs? Remember, outputs are always like 1 or 0.
Yeah, it's like
I think yes, just because there's an infinite amount. So there has to be one at least.
At least one. Okay, now before we answer this question, do you guys know why it shows a 1 here, a 0 here, 1 here, 0 here?
basically
you guys
like,
know what the
you can
pattern?
pick out all the odd numbers or even numbers. Like even number, all number will give you. I mean, the even number will give you yes, and all number will give you no, right? This is.
Okay, now that's not the pattern. So let me continue the pattern. So the next pattern, let's say this 101 program, let's say it returns a bunch of ones. I'm gonna grab that. Okay. This is supposed to be here, right? So if 101 is fed itself as that, as its own input, as input data, it would return a 1. So what I'm gonna do is that returns a 1. Could you find a program that would map 101 to 0?
But the matrix and the mapping looks is not the same, right? Like the matrix, I mean, on the this column symbol, that's the input. That's okay. But the vertical, I mean, the rows are they programs or?
Oh, right. So these are these represent programs. These numbers, these are or these strings technically.
So these are
input.
Yeah, but the input are actual things you're putting there. But the programs are just a labeling of them. Is the real program is not these numbers.
Oh, that's correct. So the real program is a graph, and these numbers here represent.
Represent just like it's like you have all the even number of programs you have. You're just categorizing them. You're counting them, right?
That's right.
So this one's 0, this one 1, this one 0, this one 1.
Yeah. So by listing these out, I'm trying to systematically sort of enumerate all the programs. So all programs can exist as sort of a string to represent the programs. And then all inputs are strings too,
Okay.
which represent whatever the programmer wanted them to represent. Okay. And then what I'm doing is I know every program on every input returns a 0, 1 or goes into an input loop. So there's this kind of two-dimensional array of all the results, right? So I'm taking this diagonal. This is called diagonalization, and I'm just changing these numbers. I'm pairing each input with a changed number on the diagonal. Why did I put a 1 here? Because that one's 0.
But that's just what you wrong there, right? It's not necessary 0, right? It could be 1.
Oh, I'm just constructing a function here, and then I'm asking, would this function be computable by any program? So in other words, since this 0 corresponds to this 0, I'm saying, could a program exist that would take an input of 0, give an answer 1? Could a program exist that would also take an input of 1? And I just made that a 0 because that's so 1. Is there a program that could take this input of 1, 0 and output a 1? And whenever this went to infinity, I just was like, is there a program that could take it 1, 1 and output a 0 there? Every time I saw infinity, I just put a 0. Every time I see a 0, I put a 1. And every time I see a 1, I put a 0. And I could do that forever because, this diagonal is infinitely long, right? And so the question is, does there exist any program that will map 0 to something that's not 0, will map 1 to something that's not 1, will map 1, 0 to something that's not 0, will map 1, 1 to 0, will map 1, 0, 0 to 1? Can any program actually achieve all those values? They're kind of like opposite values to those values on the diagonal.
I mean, I don't know. Intuitively, it seems like you could, right?
Okay, so yeah, intuitively, maybe there is a program that could do this. Okay, so what's your opinion? Is your opinion also maybe a program could compute this function?
It could if it knew what programs to compute. I think probably you'd have to run through an infinite regression to find a program that specifically could do it.
Yeah, now that's fair. Yeah, you may have to work hard because our way of encoding programs is a bit on the cryptic side. It's pretty complicated in a way. You, the programmer, trying to achieve this function, you would have to work hard to achieve it because you're kind of trying to achieve an infinite amount of very specific outputs, right?
But I mean, why thing would do that? Let's say, suppose you can do what you can do diagonal, right? Then just add one more line to your program saying, just invert whatever you got from this diagonal result, right? Like you got 1, you got 0 from there, just make it 1.
Oh, right.
So that's certainly that.
Okay, now if there was, so what you're saying is legitimate. If there was a program that could sort of accept 2 inputs, because we could basically try to run a program that takes 2 inputs. The first input is a program that the program's going to simulate. The second input is going to be like the input to that program. So we could think like this. We've got a program, and then we have a blank, and then we have some info. Could we write a program that can sort of simulate, it could read what's in memory, it could read the first bit of information, interpret that as a program. It could read the second bit of information, and treat that as an input intended for that program. And then is there a single program that can effectively simulate every possible program together with every possible input, and then that program figures out what, simulates it so it returns a 0 or 1, correctly.
I think if you had a program that could do that, then it'd just be a program that's reading the program.
Yeah, that's what it is. Can you write a program whose whole purpose in life is to read in codes that represent programs, and also read it as input and then simulate that? And it turns out if there was such a computer program that could do that, graph that could do that, that's known as not just a universal Turing machine, but this whole collection together is known. Well, it's not just a Turing machine, it's called a universal Turing machine. And it does turn out that there do exist, it's not easy to write them. It is possible to write a single program that could simulate any of these programs on any of these inputs. And that's actually what a computer really is. That is for the computer chipset of your computer. Its sole purpose, ineffectively, your computer chipsets act like a program. And what do? They run the operating system. And the operating system could be literally anything someone wants to write, right? So real computers are really what are called universal
So
Turing
the operating system essentially take whatever program can write, right?
Yeah.
And they can give you input or output. Right?
Well, that too. So user programs can run through the operating system, right? But there is a certain sense in which the operating system sort of is the program a computer really runs, and the rest is just kind of smoke and mirrors. So it's kind of like, what is a hardware chipset in a computer? It really is a it's a program, but it's all done in silicon and hardware, whose sole purpose is to run other programs which are coded as bit strings of memory, and if it needs input C. So it turns out that it is possible to write a program that could read in a program and some input and simulate that program. Now, when the program simulates a program, it will always return the right answer in this entire grid. However, what's going to happen when it tries to simulate a program that would go into an infinite loop? What do you think this universal program does? If it finds itself simulating a particular program with a particular input that would lead to an infinite,
it could kill it, or
it goes into an infinite loop too, right? I mean, have y'all ever experienced your operating system going into an infinite loop? Oh yeah, you have, right? So that's what happens, right? So that's what the simulated program's trying to do. A program that runs other programs is it'll give the right answers when they give answers, but it will also correctly go to an infinite loop with, simulating a program that goes into an infinite loop. So, but are you saying just the existence of this program means we could modify this in some way to achieve this function, this one where I've intentionally chosen values? Well, almost.
they're the trickier, because when they become infinite, right? How do you define infinity, right?
Well, infinite means the program never reaches a
but
stop.
how do you know? Like maybe this program will stop in the 10 years or something. But how the system? It's very hard for the system to see the infinity and then convert it to 0, because it's very hard to define infinity.
Oh yeah. So we don't know. In the real world, you never really know. If you see a program running seemingly forever,
we can only take like maybe a cut, like say it runs in math, like that we say whenever the program runs in math, we say that's infinity. So we'll stop it. Or it runs like how many number of loops, whatever we define.
That's right.
Then we say that's infinity.
So these infinities here in the real world, just because you see a program running for a real long time doesn't mean it's really an infinite loop, right? Particularly if you have an infinite amount of memory. In the real world, if you have a finite amount of memory, you could just look for the exact same memory state you took her.
Right, we run out of memory, so we're done.
Right, but if you have an infinite amount of memory, it literally could write to memory all kinds of patterns forever and never really stops. Okay, so you have to understand what this infinity means. This doesn't mean infinity like we think the program is going into an infinite loop. This just means this is the truth. We don't actually know the truth, but there always is a truth, an underlying truth. So this is the truth. In truth, some programs would run forever. The fact we don't know if it'll run forever doesn't mean there's not some underlying truth to it. Because this is math, right? In math, we just think like that. Okay, some of them really do go into infinite loops. But so anyway, that's actually something I did want to bring up later in the talk, is the concept that you do exist programs for sure that can simulate any program at any input. However, that's not good enough to create a function, create a program that can compute this. It turns out no program can compute this function. We'll get all these outputs. Why is there no program? Well, if you start with this program, does this program give all these values of all the inputs? You know, the input list principle kind of goes on forever.
The UTM?
No, just to erase this for a second. So this program, the program, you know, with that code.
According to what you wrote there.
Yeah, because what's the issue? This program here on that particular input gives a 0. And this function we're trying to compute, it wants the 0 to give it, if the input is 0, whether it's or 1. So no matter what this thing does on all other positions, it's not giving the correct value. What about this program here? Why is it not giving all the correct values?
Oh, because it's the diagonal element.
It's this diagonal element. So we already know that this program on this input gives a 1. That means on 1, it's not giving it.
So each one of them fails at a specific location.
Just at one spot, right?
This is kind of like contours arguments for there's always another number.
It's just like the real
infinite number of real numbers.
That's
you
right.
always construct another number that's not represented by the numbers you already know.
Yeah, so there is an argument that the real numbers are uncountable, you know, cannot be listed, they're uncountable. This is exactly the same argument, but it's a little different because of interpretation, right? This is saying no program can compute this function.
So who divided this argument?
I'm not sure who came up with
It's
this.
should be as fundamental. I mean, like contour, right? It's kind
Oh
of.
wow, this already been 50 minutes.
Yeah.
Holy cow. Well, anyway, yeah, I don't know who came up with this argument, but that's the idea, is that no program can compute this function because the first program will disagree with the function here, second program will disagree here, third program will disagree here. They'll all disagree on at least one point. So I didn't mean for this to go this long. I'm so sorry. I thought this could be a 20-minute talk.
Is
But
there a theorem or there's a present name, whatever? There's got to be some names here, right?
I could try to look it up for you.
What is the name of
just
this
read,
matrix?
I just read about this in a book. It's called diagonalization argument. They didn't even tell me in the book like who came up with the concept, right?
Yeah, but what does this have to do with our problem of PNP?
Well, it's just these P functions are a subset of all the computable functions.
Okay.
So the idea was some functions are not computable, like this weird one I just read out. Some are computable, and then some are computable efficiently, you know, and call it over time. So it
you
just
can show that NP is not in the C, but in a different set. Then it'd be like.
well, right. So last time I had all functions, then there's the computable ones, then there's the efficiently computable ones.
Okay.
See, last time we had this kind of abstract hierarchy. So this time I was trying to explain this. There are some non-computable ones. There are some functions that no program can actually compute. But there's a way more interesting result that says there does not exist a program. And I know I'm out of time, but let me just spend 2 minutes explaining this last thing. Is there a program that can figure out, given a particular program and given a particular input, is there a program that can identify if that's fated to go into infinitely or not? Does there exist a program that can analyze other programs and figure out if other programs are going to go into infinitely or not? And the answer to that turns out to be no, there is no such program that can actually, analyze other programs to determine.
This is called Turing's non-Hall.
No, yeah, this is called Turing's non-halting problem, right? And I just wanted to prove this to you guys super fast, because if you know all this that I've just done, it's pretty fast to prove. There's no such thing as a program that can, actually determine all the time correctly with other programs with the internet. So the way the program works is you start the program, somebody gives you an input. Well, okay, so first of all, we're going to assume there is a program that could take in 2 inputs. right, and determine if that program will halt or not. And then we're going to call that program, what's a good name for that program that we decide? Maybe H for halting. We'll call it H. Let's say there's a program that could take 2 inputs, a program and input, determine if that program would stop on that input. Okay, we'll see if that program exists. Now I'm going to construct another program that could compute the same non-computable function I just showed you no program could compute. How would the program work? Okay, you start. Somebody just gives you single input. It's not a programmed input. They just give you some input, right? Then this program duplicates, I'll put a D here, duplicates that input. So it takes the input and it puts a space here, and then it copies the input. Yeah, like this. Now it's got 2 identical strings, and then now we can start that halting program, that one that will take in 2 inputs, and it'll treat the first one as if it represents a program. It'll treat the second one as if it represents data, right? And if this halting problem says that that program would fed itself as data would halt, then if the answer is yes, we'll have to do a little surgery in here on its little program to to tie this in. But if the answer is yes, the program will halt, it'll run a universal Turing machine to simulate this program and that data, right? And because the program's going to halt, that universal Turing machine is going to it's going to simulate the program correctly and give a correct answer. 2 answers it could give are 0 and 1. If we see, so we let that universal Turing machine that simulates other programs run, and if it says that that program would give a 1, we'll write a 0 and output a 0. And if that universal Turing machine simulates that program and says it would return a 0, we'll go ahead and write a 1. So that is what we're trying to do here. We're trying to do the opposite. We're trying to output the opposite, what that program would output if we hadn't added in this last little bit, code here. And then if this halting program says no, well, we don't want to simulate something that's going to go into an infinite loop because that would cause this to go into an infinite loop. So if this says no, we'll just write a 0 here and we'll stop. And the question is, does this program always halt? This one that uses these little sub-programs of universal Turing machine, halting program?
It seems so. I mean, there's no arbitrary, ambiguous ambiguity here, right? Like
That's
yes
right.
or no, and then each time it goes to 0.
Yeah. If it'll take some input and it'll copy it, and then it'll ask if I were to run that program on that data, would it go to infinite loop? And if it wouldn't, oh wait a minute. Sorry, this is all backwards. If it won't go into the infinite loop, we'll go and simulate the program and output the opposite thing to that program. If it would go into the infinite loop, then this program won't, because it'll go ahead and stop it right there. And anyway, what goes on is this program here I just wrote, this will compute that non-computable function that no program can compute, because it likes to do this contrary thing. It likes to do the opposite along that diagonal, So this program doesn't actually exist, but universal Turing machines exist. So do programs that duplicate entries. What's wrong with this is there's not actually a halting program.
But you didn't prove anything, right? You
Yeah.
assume that H exists, and then you show that everything. You should have to come with some contradiction.
Oh yeah, the contradiction is if H exists, if a halting program exists, then this program exists. And if this program exists, if you look at how this program works, it just simply computes.
Okay, so you're saying this violates this diagonal.
Yeah, this program exists. If you look at what this program does, it actually computes a function we know is not.
Yeah, that kind of the thing I want to do. But, yeah.
This computes a non-computable.
The diagonalization argument is essential for this non-halting.
Yeah, that's right. At least this particular proof, it's a kind of standard proof of the non-halting.
The reason H doesn't exist is because you would need to program before you get H.
No, basically the argument is you have to accept the diagonalization argument. if you accept that argument, then he's trying to disprove by contradiction.
Well,
Right, is that right? Is that one?
yeah, what you're saying is essentially right. Basically, if there was a now you're right, it would be very hard to write a program. It seems intuitively like it would be pretty difficult to write a program that can always take in a program and its potential input and figure out, is that fated to go into an input loop? It seems like it's really hard to write that just intuitively. But this argument is trying to argue that it definitely can't, a program like that can't be written no matter how clever someone is. Why not? It's because you could basically, this program here will basically, for every input, it will, so remember, an input of 1, it will calculate it for an input of 0, it'll calculate something contrary to what program 0 would do on an input of 0. On an input of 1, it will calculate something contrary to what that program would do, you know, if it was fed itself with data. So that's what this program does. If you read it carefully, you'll realize, yeah, it actually computes a non-computable function word computes.
So
no
what is
program.
the name of the book, Alice?
Oh, I'd have to go look it up. I don't
You
remember.
remember?
Yeah, I don't remember. I just read it. So sorry this is so long. This is
No,
over
I'm sorry,
60
I
minutes.
have to leave to pick up my kids or something. So
Sure.
can we, let's thank Dr. Bubbles for.
Yeah. So like again, sorry I meant this to be 30 minutes. But so yeah. So if you have any questions about any of this stuff, just feel free to email me if I made any mistakes. If you have any, feel like there's some mistakes in here, just tell me, email me and I'll try to fix them for you.
Okay, great. Let's stop the record.